All right, this is page number 6. So, question 7. The second of what waves do. Waves will interfere with each other. They also reflect, but that gets more into standing waves, that they will interfere with each other. So, if I've got two waves, they can either constructively, so make a larger energy pulse if they're both in the same direction, in phase, we call that. Or if they're out of phase, one is maybe a down pulse and the other's an up pulse, or one's a compression and the other's a rarefaction. They can actually cancel each other out and you get destructive interference. Now, there's something called beats here, which is a kind of extension of that. We didn't talk a lot about that, but I'll show you how to do that. And it's not that important for this particular one. It's just an application of interference here. So anyway, though, but we do need to analyze this wave here. So I've got two waves, a red and a blue one here, kind of a higher frequency and a lower frequency red one, and different points along this timeline probably of what different types of interferences are happening at different times. So at point A, what type of interference is occurring? Well, I see this is an up pulse and this is a down pulse. So that is going to be destructive interference at point A. Up and down will cancel out. At point D, I see the blue one is down and I also see the red one is down. So since they're both down, that's going to be constructive interference. It's a little confusing, like, well, that's downwards. That doesn't matter which way they are, up or down. If they're in the same direction, they are contributing to each other's energy and they will make a larger combined energy from that. Point B would also be constructive interference. So both D and B are constructive interference here. Likewise, A and C would also be destructive interference up and down. All right. So then we get to this idea of beats. Beats, when two frequencies are fairly close to each other, not the same, but fairly close, they don't perfectly overlap. And sometimes, so since they're slightly different, eventually they're going to contribute constructively to produce a high, like a louder sound. And then they're going to later on in their wave are going to construct a destructive and kind of cancel each other out, producing an underlying beat frequency, which is much, much lower than that. And it's just the difference between the two frequencies. So if I want to calculate the beat frequency is just frequency 1 minus frequency 2. Technically, it's the absolute value. We want to ignore the negative here. And so if there's 248 and 254, 3, let's erase that. 348 minus, we'll do the absolute value, 354, I get a beat frequency of 6 hertz. Notice 6 hertz is much, much lower than the other two frequencies. So the other two would still make their kind of A note, or let's see, 3, 4, C, A, B, C. I'm not sure that, maybe a G note. I'm not sure the exact frequency of those. But they would produce, since they're slightly different, it would produce a 6 hertz. And this is actually how you can tune an instrument. If you can hear one instrument that's in tune making the appropriate frequency and yours is out, you will hear a beat from your instrument, and you can change it to make that not a beat anymore. And so if you're in tune, you don't hear that beat. All right. What frequencies, when paired with a 348, would make a 3 hertz? So we need 3 to be the difference, absolute value of 348 minus some other frequency. Well, there's two options for this since it's absolute value. It could be 345 hertz. All right, 348 to 345 is a 3 difference, or we could go up from that, and 351 could also make a frequency here. So either one will give the difference of 3 hertz. Again, I don't know, I'm not going to star it. We didn't do a lot of that in class, but it is pretty simple. Beat frequency is just the difference between two frequencies that are very close to each other. All right. Let me get to the idea of harmonics and different frequencies on the same instrument. This is called a fast Fourier transform, but more importantly, you just need to see that they have certain frequencies within a wave. So what's the fundamental frequency of this note? Well, this particular one, the fundamental is the lowest, so that's going to be 100 hertz. What harmonics can we see? We can see 100, 300, and 400. So that is 100, 300, and 400. And then the last one asks which what harmonics are those? Well, if the fundamental is 1, the fundamental frequency is 100. Oh, sorry, 100 hertz. Then the 300 will be the third. So that's the first harmonic. The 300 will be the third harmonic. So this is n equals. And then 400 will be the fourth harmonic because it's just multiples of that fundamental. So the harmonics would be the first, the third, and the fourth harmonics there. All right. That is interference.